Lesson 8-1, exponential functions. First off, what is an exponential function? An exponential function is just a function in the form of y equals a times b to the x power, where a cannot equal 0, b has to be greater than 0, but it cannot be 1. One reason why it cannot be 1 is if the base is 1 and you raise it to exponent, 1 to any power is always going to give you 1. So it can't be 1 because otherwise it doesn't change anything. And it can't be 0 because if you raise 0 to anything, it's just going to be 0. And there wouldn't be an increase or a decrease on that one. Notice that the base is a constant and the exponent is a variable. Exponential functions are non-linear. So when you are substituting values in, you're substituting values in for x. And that would be your independent variable. And whatever your base is, you raise it to the power that you choose. It will give you a nonlinear function in the end. So an exponential function, here what it describes the example. We have y equals 2 times 3 to the x power. 3 is the base. That's the common ratio. So with exponential functions, you are going to have a common ratio. Here's another example, y equals 4 raised to the x power. You'll notice that there's no a in here. Technically there is, it's just a 1, and so they're not putting it in there. And then we have another one, y equals, our base is half raised to the x power. So our base can be a fraction, it just can't be negative or equal to 1 or 0. While exponential functions does not have a constant rate like a linear function does, it does have a common ratio. As I said, our b in our function y equals a times b to the x power is our common ratio. So the data set can be modeled by an exponential function if for equal intervals of the independent variable, the dependent variable increases or decreases by a common ratio. So what that is telling you is that your x coordinates must increase by 1. And if your x increases by 1, then your y should increase or decrease by the same ratio. It just means you're multiplying by the same factor each time. So how do you find the common ratio? To find the common ratio, you take the y value, pick one of the y values, and divide it by the previous y value. And the ratio must be the same for each interval for it to be an exponential function. So if we compare linear and exponential here, on the left-hand side we have linear. You can see that it increases by a constant rate, so it has a specific slope. So in this case it's a 1, so it goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Our slope is 1. But on exponential, you can see that the slope changes, but it increases by the same factor. So you're multiplying, and in this case, you're multiplying it by 2 every single time. And so the further to the right you go, the bigger the jump is going to be. Let's take a look at an example. The Richter scale measures energy that an earthquake releases inside a magnitude to it. These orders of magnitude can be approximated by comparing them to the explosive power of TNT. Determine whether the set of data can be modeled by an exponential function. So the first thing I want to check is my magnitude, which is my x variable, my independent variable. Are they increasing by 1 each time? And yes, they are. So that is a good sign for this to be possibly an exponential function. Now, to determine if it's got a common ratio, I'm going to pick a y value. I'm going to pick 60. And then I'll have to divide it by the previous one, which is 6. 60 divided by 6 is 10. So that means if I were to multiply every y value by 10, I should get the next value below it. So if I did 0.6 times 10, I should get 0.6. And then if I multiply that by 10 times 10, I should get 60. 60 times 10 should give me 600. 600 times 10 should give me 6,000. And you'll notice that I'm just adding a 0 each time, which means I'm multiplying by 10 each time. So is this a exponential function? Yes, we would say it is a exponential function, and it has a common ratio of 10. So here, if you wanted to go a little bit more in detail, you're just comparing modules 1 and magnitudes 1 and 2 like I did before. But here you just do 6 divided by 0.6. Remember, you can't divide by decimals. So if you move the decimal point over, do that in numerator and denominator, that ends up being 60 divided by 6, which is 10. And then magnitudes 2 and 3, that would be 60 divided by 6, which was 10. And 4 and 5 would be 6,000 divided by 600. This would also be 10. That's just another way to verify that. Second example. In the 19th century, psychologist Hermann Ebbinghaus created a formula to approximate how quickly people forget information over time. The approximate percentage of the newly learned information a person retains over time is shown in the table. Determine whether the set of data can be modeled. So the first thing I want to check is, are my days increasing by 1? And each of these is increasing by 1. So that is a good sign there that this could possibly be an exponential. Now I need to check the percent retained. Does that increase or decrease at a constant rate? So I'm going to take the 80 divided by the previous one, which is 100. If I divide that in half, that gives me 0.8. Next one would be 64 divided by 80. If I do 80 divided by 64, or 64 divided by 80, I end up with 0.8. So far, so good. And if I did 51 divided by 60, 51.2 divided by 64, so 51.2 divided by 64, I get 0.8. And if I did 51. So I'm going to change, I'm going to do 51.2 times 0.8. See if that still gives me 40.96. That does, and then if I take 40.96 times 0.8, that gives me 32.768. So according to the numbers I was using, this is showing an exponential function. So we would say yes, and our common ratio is 0.8. After World War II, the television became a major consumer product in the United States. The percentage of households with TV for each year in the 1950s is provided in the table. Determine whether the set of data can be modeled by an exponential function. So I checked my years. Are they increasing by 1? Yes. Now the percent of households with a TV. One thing you can check to see if it's an exponential or not, too, it's not a guarantee, but if you look at the numbers, are they increasing rapidly or are they decreasing rapidly? In this case, you can see that a lot of these numbers are very close to each other. So they're not really increasing rapidly. But to verify it, let's take 24 divided by the previous one, which is 9. And 24 divided by 9 would give us roughly 2.7. It's 2.6 repeating. Now if I did 34 divided by 24, 34 divided by 24 gives us roughly 1.4. So those are not the same. And because they're not the same, this is not an exponential function. Second part is graphing of the exponential functions. So functions of the form of f of x equaling a times b to the x power, where a is greater than 0 and b is greater than 1, are called exponential functions. This could also be, so it would be if the b is greater than 1, it's going to be an exponential growth. And then if the b is between 0 and 1, it's an exponential decay, which just means it goes downward, it's decreasing. The graphs that you're going to have for an exponential function are going to have an asymptote. These asymptotes are just boundary lines that the graph approaches but never touches. So in the example down here, you can see that our asymptote is actually going to be the x-axis. It will never ever touch, make y equal to 0. Let's take a look at some of the graphs for a growth and a decay. For a growth, it's going to go up from left to right. So from left to right, it's going to go up, it's going to increase. And then for a decay, it's going to go down from left to right. And it's all going to be based on, you can determine that by looking at the b in the equation of f of x equaling a times b to the x power. So example 2, graph each function and determine whether it represents the exponential growth or exponential decay. So this first one, I'm going to look at my b here. My b is 2. Since 2 is bigger than 0 or bigger than 1, I know that this is going to be a growth. And the other one, this is less than 1 but greater than 0. This is going to be a decay. Now, how are we going to come up with the points to graph this? So we can create a table of values. So let's do here's our x and here's our y. I'm going to choose some easier numbers. We'll use -1, 0, and 1. So if I put that in for the first one, I would have 2 to the negative first power is 1/2. Because remember, anything to the negative exponent, you do the reciprocal of the base. So that would give me 1/2, and then multiply that by 5, which will give us 2.5. 2 to the 0 power is 1. 1 times 5 is 5. And then 2 to the first power is 2 times 5 is 10. So if I come over to my graph and I plot those points, I'm going to use red for this one. So f of x is going to be red. So I have -1 and 2.5. -1 and 2.5 would be roughly here. 0 and 5 would be here. And then 1 and 10 would be here. If I wanted to go further, if I were to go, let's just say I did 2 raised to the -10th power, multiply that by 5, it gets me a really, really small number of 0.0048 and so on. But as long as I have these points listed right here, I can now take my graph. I know it's not going to touch the x-axis. Right, so gradually going to get higher and then it goes up pretty quickly here. So that would be the graph of f of x. Now I'm going to use blue for this other one. So we got x and we got y. And I'm going to use the same points for this one. I'm going to use -1, 0, and then 1. So 1/2 raised to the negative power is 2. So the reciprocal of half is 2. And then 2 times 5 is 10. And then half to the 0 power is 1. 1 times 5 is 5. And then half to the first power is half times 5 will give us 2.5. So if I plot those on here, I would have -1, 10 be up here, 0, 5 would be here, and then 1 and 2.5 would be here. And then I can draw my line. This one comes down, and then eventually comes across close to the x-axis. Across the x-axis. Next, graph each function and determine whether it represents an exponential growth or an exponential decay. So I know this first one, the b is less than 1 and greater than 0, so this one is a decay. This one, the base is 2, which is greater than 1, so this is a growth. But this one I'm going to graph on my graphing calculator. We'll grab our calculator here. We hit our y equals, and I'm gonna put both of them on the same one. So I'm gonna do 4 times the parentheses 1 divided by 2, or you can use 0.5, and parentheses raised to the x power. And then the other one, I have 4 parentheses 2 raised to the x power, and parentheses. And if I hit zoom, number 6 for standard, you can see there's the first one, that's the decay, and then here's the growth. That one looks very similar to the one we drew before, just a little bit slightly different because our A is a little bit big, is smaller on here. That's how you could do it on your graphing calculator. Next, graph this one here. I will do it back on the coordinate plane here. The B is less than 1 but greater than 0, so I know that this is a decay. Then let's draw a table of values. Here I will use do negative 1, 0, 1, and then I'll do 2. Plug those numbers in. So 1/3 raised to the negative first power is 3. 3 times 2 gives us 6. 1/3 to the 0 power is 1 times 2 is 2. 1/3 to the first power is 1/3 times 2 is 2/3, which would be 0.6 repeating. And then if I raise 1/3 to the second power, that would give us 0.1 repeating. Multiply that by 2 gives us 0.2 repeating. Now if I were to graph this one on my coordinate plane, I would have negative 1, 6 here, 0, 2 here, and then 1.6 would be roughly here, and then 0.2. So it gets closer and closer, but it never touches. Goes down, and then it gets closer and closer to 0, but never reaches 0. So that is our lesson on exponential functions.